In this video, we are going to look exclusively at what a does. So notice that a is being multiplied in front of the x squared. So if we look here at our vertex form, we can see that a is what's being multiplied in front of that parentheses that contains the x. So we can see here that it talks about it being a vertical stretch where a is greater than 1, and here is a vertical compression where a is a fraction between 0 and 1. Before we get started, I want to make sure you write in the end for compression in case this didn't print. Also on the inside, I went ahead and I color-coded everything ahead of time like we have been doing. So you should do that as well. Also make sure that you have written in all of the possible print that may have gotten cut off on the left margin. The other thing that you need to do is you need to put in the y value for the parent function of y equals x squared. I would do that for both the stretch and the compression. And I also already put in what my parent function would look like. So you should go ahead and do all those things before I continue. So let's go ahead and look at transformation of the parent function when a is 2. So just note that that is bigger than 1. So I'm going to put 2 here. My h is 0. My k is 0. So when I clean this up, x minus 0 is just x, and that's all squared. If I add 0 on to the end, imagine a plus 0, it doesn't add any value, so I'm not going to put that there. But this is now being multiplied by 2. So now I have 2x squared. We've not seen something other than 1 before, so let's see what happens here. We should easily be able to get the vertex because nothing is being added to this x, so that's my h, and nothing is being added on to the end of the function, so that's my k. And in fact, we have it right here. So let's see what sort of transformation we have. So this is saying whatever x squared is, I'm going to double it. So all of these values are x squared. So if I do 2 times 9, so if I do 2 times 9, remember because this is 2 times x squared, that gives me 18. 2 times 4 is 8. 2 times 1 is 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 4 is 8. And 2 times 9 is 18. So once again, I want to point out the symmetry. Here was our vertex for our parent. This is also our vertex for our transformed function. So just notice how to the left of 0 it goes 2, 8, 18, and to the right of 0 is 2, 8, 18. It's a nice balance on both sides. So let's go ahead and graph this and see what happened. So I still have my 0, 0, but here at -1, I now have 2. At 1, I have 2. Notice how those points are inside my parent function. So my function's gotten skinnier. At -2, I have 8. And at 2, I have 8. So I cannot plot -3, 18, because 18 is way up here somewhere. It is off of my graph. So notice It got narrower. Okay, this is still curved here at the bottom. So what I want to point out is the function got narrower or skinny. Okay, so we say that this is a stretch. So what I want to show you is I have a rubber band. So if you pretend that's the parent function, notice the letters on the rubber band. As I stretch it, notice how they get stretched up and down, and the letters are getting skinnier left to right. So just look at that. Look at the O in fox. Notice how that O in fox is getting skinny and taller. And do it again. That O in fox, just the O, is getting skinnier and taller. Okay? So that's what's happened here. It's gotten skinnier than the parent. So we don't write skinnier when we're talking about a stretch. We just say it's a stretch. But let's go ahead and write gets narrow or skinny. Okay? And that's when A is bigger than 1. So this here has to be, so this here could be, I'm going to say it could be 2, but it could also be a fraction like 3/2, because 3/2 is 1 and 1/2, so that's bigger than 1. Okay? So it doesn't have to always be an integer. It could also be a fraction, as long as that fraction is bigger than 1. So let's go ahead and look here. Oh, before I do that, remember before we talked about a reflection. So a stretch could also include -2 or even -3/2. These are just examples, okay? But what I want to point out is that this number here is what's causing the stretch. Oops, I left my pen. So this here that's highlighted, that's the stretch, and that negative there is the reflection over the x-axis. So you can have more than one thing happening with that A. So the A can also give us a compression, and that's when we have some number between 0 and 1. So the example that I gave you here, just because it's easy to deal with, is where A is 1/2. So the same sort of thing happens here. I'm going to put 1/2, H is 0, K is 0. When I clean this up, I get 1/2 x squared. My vertex is 0, 0, because there's no parentheses with something being added or subtracted to x. So my h is 0. I don't have a plus or minus something here at the end, so my y is 0. So this is my vertex. This is my hk. Remember, hk is a special xy. So let's see what happened here. So remember, my new function is 1/2 x squared. So that means I'm going to take 1/2 of x squared. Well, these numbers here are all x squared. So 1/2 of x of 9, I'm going to write it as 9/2. Yes, that's the same as 4.5, but we're going to keep it as 9/2. Half of 4 is 2. Half of 1 is 1/2. That's the same as 0.5 or 0.5, but we're going to write 1/2. Half of 0 is 0. Half of 1 is 1/2. Half of 4 is 2. And half of 9 is 9/2. Okay, so I'm really not going to plot fraction values, but that gives us an idea of where it will be. So we'll probably kind of plot that, but know that it's not accurate. That's just helping us know how narrow or fat our function is going to be. So once again, I already have my parent function graphed. Let's start from the vertex. So we know that the vertex of the parent function is 0, 0, and the vertex of our new function is 0, 0. So we're going to start with that. So let's plot 0, 0, which is right here. And then 1, 1/2, I'm not going to plot that. I'm going to go to 2, 2. So here, 2, 2. Oh, shoot, I'm going the wrong way. Sorry. Thinking of reflection. 2, 2 is here. And negative 2, 2 is here. I'm glad I caught myself. It's easy to do. So you can see right now it's getting fatter, right? And if I were to go to 3, that would be 4/2, which is about here, but I'm not going to plot it. What I am going to do is, let's go to the next one here, which would be 4. Okay, so if I'm sorry, I'm not thinking. Yes, x is 4. So let's put 4 here. 4 squared is 16. So in our new function, if I were to take half of 16, I get 8. So where x is 4, I get 8. So let's do that over here. Where x is 4, I get 8. Okay, so remember, because this is symmetrical, I don't have to do negative 4. I know it is 1, 2, 3, 4 out from that axis of symmetry. So I'm just going to do the opposite direction. 1, 2, 3, 4. So we can see, ignore that needs to be whited out. That our new function has gotten wider. So the function got wider. Now I can't show you what that would look like on my rubber band because I would have to squish it, and I can't quite squish that rubber band to make it do what I want you to do. But if this is a stretch where it got skinny and tall, if it gets wider, that's a compression. So what I want you to think about with a compression is you're pressing down the ends of that parent, and as you're pressing it down, it gets fatter. So let's look here. So here we have the word press in compression. So that means it gets wider. So when you press something down, it gets wider. If I had silly putty, I would take a ball of silly putty and press it down, and you would see that it starts getting wider and smushed out. So this here is a number between 0 and 1. So I already showed you 1/2. It could be 1/4. It could be 3/4. It could be 5/8. These are all numbers between 0 and 1. And again, if I put a negative in front of any of these numbers, it is still a compression because this here, these negatives, is simply a refraction over the x-axis. It would just be flipped upside down. And that's what I was thinking here. I got mixed up. So this point does not exist. That's wrong. It was a mistake. Okay, so I'm going to show you some tricky things with vertical stretches and compressions.